Hello, and welcome to my video on photoacoustic spectroscopy. I'm going to try to hit most of the basics in this video. The photoacoustic effect is a photothermal effect that involves a substance absorbing modulated radiation and then releasing that energy to make a sound. When a substance absorbs radiation, its molecules will expand. Subsequently, its molecules will release their energy thermally by contracting. The resulting pressure differential makes sound waves. See here, light is absorbed by the analyte expands, and then it will contract as it releases the energy thermally, which produces sound waves, like the one shown here as a pink ring. The photoacoustic effect is the driving force of photoacoustic spectroscopy. The radiation must be modulated so the molecules may expand and contract repeatedly, and the radiation must be intense enough to give adequate sensitivity to the spectroscopy. Furthermore, since different substances absorb light at different specific energies, photoacoustic spectroscopy can be used qualitatively to determine the components of a gas, liquid, or solid depending on the wavelength absorbed. To achieve pulse high-intensity narrow wavelength, a tunable laser is usually used for the spectroscopy. Very sensitive microphones are used to obtain precise detection of sound waves. Additionally, the frequency of the pulses can be changed to match the resonance of the sample chamber, and devices called lock-in amplifiers can be used to reduce background noise to produce even better signals. Given this accurate method of detection and high-intensity radiation source, photoacoustic spectroscopy can also determine concentrations of substances in a sample. Infrared spectra are mostly made with the spectroscopy, and a Fourier transform is applied to the output. As you can see, on the photoacoustic spectrometer there is a laser that shines into the sample holder. It can be directed onto a solid or liquid, or simply into the chamber of gas. Between the laser and the sample container, there is sometimes a spinning fan-like object that blocks light and then allows it to pass through repeatedly. This allows the analyte to expand and contract repeatedly to make the sound waves necessary. Microphones hooked up to the lock-in amplifiers pick up the sound, and the data is processed by the Fourier transform in the computer. As it turns out, photoacoustic spectroscopy can be used to detect very small concentrations of gases down to the parts per billion and even parts per trillion. But as stated earlier, photoacoustic spectroscopy is not only for gases. It can be used to analyze blood, skin, eye lenses, tumors, and even drug-laced tissues. Also, it can be used on other liquids and solids. In the case of analyzing liquids and solids, the sample chamber is filled with a high thermal conductivity gas such as helium or nitrogen. Probably one of the largest advantages of this spectroscopy is that it can analyze a sample without dissolving or disrupting the sample in any way. The sample can be placed in the sample cells that already exist. Photoacoustic spectroscopy has a large advantage over other methods of producing spectra for solids because other techniques suffer from light scattering and reflection. Currently, research is being done to make both highly sensitive and accurate spectrometers and less sensitive, cheap, small, portable versions of the photoacoustic spectrometer. These small spectrometers could be used by troops to detect trace amounts of toxins in the air on the battlefield. Drawbacks to this spectroscopy include that it best operates by scanning through at one wavelength at a time and can only identify one substance each run, and this process takes time. However, many scientists are finding ways to speed up this spectroscopy by making devices that can detect and distinguish between multiple chemicals at once. In a specific example of recent research with photoacoustic spectroscopy in an article entitled Quantum Cascade Laser-Based Photoacoustic Spectroscopy for Trace Vapor Detection and Molecular Discrimination, to detect low concentrations of gases, researchers formed microelectromechanical systems, MEMS, to be used alongside mid-infrared quantum cascade lasers, QCLs. Their experiments involved obtaining the acoustic spectra of acetone, vinyl acetate, acetic acid, and 1,4-dioxane. But that was not their end goal. Their goal was to develop a method that simultaneously distinguished the four spectra from each other. They called this method of scanning the spectrum from 1050 inverse centimeters to 1240 inverse centimeters a multivariate analysis. This figure shows that, like many instrumental methods, the signal detected by the microphones increased linearly with the concentration of the analyte. This next figure shows that each analyte has a distinct signal, as can be seen in the graph. Also, you see a Fourier transform is used to process the data. This figure shows each of the four spectra in the experiment superimposed on each other. Notice that they all have distinct features. The researchers developed MEMS that could differentiate and separate the spectra all at once. The photoacoustic signal is additive, and the computer recognizes the distinct features from each of the substances in its library to decide exactly how much of each analyte is present. On top of the amazing things that this system can achieve, it does it all while being relatively small. This table depicts the accuracy of the photoacoustic spectroscopy's ability to simultaneously predict the concentration of the four components. The researchers used predictive algorithms to determine the concentrations very accurately in the parts per million range and reasonably accurate in the parts per billion range, considering that four chemicals were being detected at once. You can look here in sample number 7. They had some acetic acid, some acetone, and some vinyl acetate. And the spectroscopy predicted pretty close for each of these three. And look, it even said there would be no 1,4-dioxane, and it got that right. So it can be seen pretty clearly here when detecting multiple analytes at once that the data obtained can at least be used qualitatively. And with more work on their algorithms, I'm sure the quantitative analysis abilities for the spectroscopy can be further improved. I hope this was helpful. Thank you very much.